Welcome to the MOOCs course Advanced Thermodynamics. The title of this lecture is Solid Liquid Equilibrium Part 2. Since it is a continuation of our previous lecture on solid liquid equilibrium, we will be having a kind of recapitulation of what we have studied in the previous lecture. Okay. So, in the previous lecture we have taken different SLE problems where pure solids in equilibrium with liquid, then what is the corresponding phase diagram, that is what we have seen, and then corresponding equilibrium relation in order to find out the equilibrium composition for such case of pure solids in equilibrium with liquids, those things also we have developed. And then analogously phase diagram of partially miscible solids in equilibrium with liquid, those things we have seen. And then for such case also we have seen what are the equilibrium relation that can be used to obtain the equilibrium composition for the case of partially miscible solids in equilibrium with liquid as well. Those two cases we have seen. So, that is phase diagram of pure solids and then solid solutions in equilibrium with liquid have been discussed. Then corresponding equilibrium equations have also been established. For pure solids we have obtained this information, that is ln xi gamma I is equals to delta G fusion by RT, that is delta H fusion by RT minus delta S fusion by R, but in general this delta H fusion and delta S fusion are available at standard temperature, something like at melting temperature, etc. So, but we need at certain temperature, any temperature T. So, what we have to do? We have to construct a thermodynamic pathway and then obtain this information at any other temperature T as well. That is what we have done. So, when we have done that one, then we got this expression in the previous lecture, that is ln xi gamma I is equals to delta H fusion at temperature Tm divided by R multiplied by 1 by T minus 1 by Tm minus 1 by R integral delta Cp by T dt from Tm to T plus 1 by RT integral Tm to T delta Cp dt. So, if you assume this delta Cp as a constant and then do integration, substitute the limits and then do some kind of simplification, then for ith component we got this relation, that is ln xi by gamma I is equals to delta H fusion at Tm by R multiplied by 1 by T minus 1 by Tm I plus delta Cp by R multiplied by 1 minus Tm I by T minus ln T by Tm I. This is what we have seen. This is for the pure solids, that is even the solids are being transferred into the liquids, liquids are not transferring into the solid phase. So, even during the course of species transfer, the species solid species are remaining pure, solid species remaining pure, that is capital Xi is remaining 1, maybe their weight may be decreasing or amount may be decreasing because they are transferring to the liquid phase. Okay. We have seen in the previous lecture capital Xi we have indicated for the mole fraction of component I in the solid phase, and then small xi as usual we have taken the mole fraction of component I in the liquid phase. So, in the case of pure solids we have this xi is equals to 1 always. Okay. So, that is what we have done, but in general there may be a kind of partial miscible solutions also, then this xi cannot be equal to 1. So, for such conditions also we have developed these relations. For partially miscible solid solutions we have FIS is equals to FIL, then we have capital Xi capital gamma I FIS is equals to Xi gamma I FIL. Capital Xi is nothing but the mole fraction of component I in the solid phase, and then capital gamma I is nothing but the that indicate or display the non-ideality in the solid phase, and then FIS is nothing but the fugacity of that component I in the solid phase at certain reference conditions, whereas small xi is nothing but the mole fraction of that component I in the liquid phase. Gamma I is nothing but the activity coefficient of that particular component in the liquid phase, which indicate the non-ideality of the system, and then this FIL is nothing but the fugacity of component I in the liquid phase at certain reference conditions. So, now this we can write it as small xi gamma I by capital Xi, capital gamma I is equals to FIS by FIL, and then for this one also, in the case of pure solids in any equilibrium with liquids, whatever the way that we have followed for the derivation of equilibrium relation, if you follow the entirely the same pathway here also and do the simplification, then you get this ln of this, then you get this relation ln of small xi small gamma I divided by capital Xi capital gamma I is equals to delta H fusion at Tm divided by R multiplied by 1 by T minus 1 by Tmi plus delta Cpsl by R multiplied by 1 minus Tmi by T minus ln T by Tmi. So, only difference compared to the pure solids case is this additional thing is coming here. Capital Xi and capital gamma I are coming into the picture in the case of partially miscible solution. Whereas, in the case of pure solid solutions in equilibrium with liquids, then this capital Xi is equals to 1, and then if it is a pure solid, then it is a kind of ideal solid. So, then capital gamma I is also equals to 1. Remember, ideality in the case of solids is defined in the similar way as in the case of liquids. That is, if the component is pure, then or if the component is almost pure, then we can say that is a kind of ideal system. So, if the solids are partially miscible, so then they are not pure solids, so then obviously they are not ideal, so there would be some capital gamma I information as well, and then Xi cannot be 1, so there what is that Xi that we have to find out in general. So, this is what we have seen, and then corresponding phase diagrams for either of the cases also we have seen in the previous lecture. Now, what we do? We take a few example problem based on the discussions that we had in previous lecture, so that we can find out the equilibrium composition or eutectic composition, etc., or how we can make use of these relations to get other kind of information. Those things we are going to see in the form of a few example problems. So, example 1. The excess Gibbs energy for a binary mixture of liquid A and liquid B is given by GE is equals to 6000 XA XB multiplied by 1 minus 0.0005 T joule per mole, where T is in Kelvin. The solids are completely immiscible. The enthalpies of fusion and melting temperatures for either of the components are given. For component A, delta H fusion is minus 12 kilojoule per mole, and then melting point is nothing but 1000 Kelvin, whereas for component B, delta H fusion is nothing but minus 10 kilojoule per mole, and then melting temperature Tm is nothing but 800 K. Now, determine the temperature and the composition at eutectic point, but neglect delta Cpsl. So, delta Cpsl, that is Cps minus Cpl, is 0. So, solution: since solids are completely immiscible, then FAS is equals to Xa gamma A FAL, and then FBS is nothing but Xb gamma B FBL. So, then we have for completely immiscible system, that means system is pure system. That means solids are remaining pure solids. They are completely immiscible, so they are completely pure. So, then we have that capital Xi is equals to 1, and then capital gamma I is also 1. Then whatever the pure solids in equilibrium with liquid case is, that expression we have to use. So, that expression is nothing but this one, that is ln Xi gamma I is equals to delta H fusion at Tm divided by R multiplied by 1 minus T minus 1 by Tmi plus delta Cpsl by R multiplied by 1 minus Tmi by T minus ln T by Tmi. But in the problem it is mentioned that delta Cpsl is 0. So, the second term is not going to be there, and now this expression if you write for two components, so that is component A and B. So, ln Xa gamma A is equals to delta H fusion Tm by R multiplied by 1 by T minus 1 by Tma, and then this ln Xa gamma A I can write ln Xa plus ln gamma A, and then Xa I am writing 1 minus Xb. So, ln of 1 minus Xb plus ln of gamma A is equals to right hand side as it is. So, now Tmi in place of I am writing A. Similarly, for component B, if you write ln XB gamma B is equals to delta H fusion at Tm divided by R multiplied by 1 by T minus 1 by Tmb for component B. So, here also ln XB gamma B, I can write ln XB plus ln gamma B. So, then we have right hand side as it is without any change. So, now we have to solve this equation actually. These delta H fusions are given for both the components, TMA, TMB are also given. So, we have to find out these temperatures and then this XB composition. So, two equations or two unknowns are there, but what is this information? Activity coefficient, that we do not know, but excess Gibbs energy, molar excess Gibbs energy information is given, expression is given. So, that is we can use that expression to get this ln gamma A, because we know RT ln gamma A is equals to minus Ga bar E. So, that is Ga bar E is nothing but dou by dou Na of Nt, and then whatever Ge is given at constant temperature, pressure, and then Nb, if you do that, you can if you find out this differentiation, whatever Ge that is given, that Ge you write in terms of moles, Ge is given in terms of mole fraction, that you write in terms of moles, and then multiply by total number of moles Nt, and then whatever that product is there, you partially differentiate with respect to Na. Then again you convert that expression in terms of the mole fraction. So, that you get this one. These things, so many examples we have done in LLE case. So, similarly when you do this, you get. So, that RT ln gamma A is nothing but 6000 multiplied by 1 minus 0.0005 T XB square. So, from here ln gamma A is this one, that is 6000 multiplied by 1 minus 0.0005 T XB square by RT. Similarly, RT ln gamma B is nothing but Gb bar E. So, that is Gb bar E is nothing but dou by dou Nb of Nt Ge at Tp Na. So, whatever Ge expression is given in the problem, that is given in mole fractions, you convert in terms of moles by taking Xa is equals to Na by Nt and Xb is equals to Nb by Nt. Then whatever the Ge expression in terms of moles is there, that you multiply by Nt. So, whatever the product expression is coming, that you partially differentiate with respect to Nb. So, then whatever the final expression that comes in terms of moles, that again you convert in terms of mole fractions, then you will get 6000 multiplied by 1 minus 0.0005 T multiplied by 1 minus xb square. You get xa square, but 1 minus xb square you can write, and then that part is nothing but equals to RT ln gamma B. So, ln gamma B is nothing but 6000 multiplied by 1 minus 0.0005 T 1 minus xb whole square by RT. So, now this expression you can write here in place of ln gamma A, and this expression you can write in place of ln gamma B here. Then what you have? You have this expression ln 1 minus xb plus ln gamma A is nothing but 6000 multiplied by 1 minus 0.0005 T xb square by RT is equals to right hand side is as it is for the component A. Similarly, for the component B, ln xb plus ln gamma B is nothing but 6000 multiplied by 1 minus 0.0005 T x A square. So, that is 1 minus xb whole square divided by RT, and then right hand side is same as it is for a component B. So, now only thing unknown is in these two equation is the temperature and then this xb. So, we have two equations, two unknowns. So, when you solve these two equations, you can get whatever the temperature and then xb, that we get as this. Temperature you get 656 Kelvin and then xb you will get 0.66. So, that means eutectic composition or the composition at the eutectic point is nothing but Xa is equals to 0.34 and then xb is nothing but 0.66. Okay. This is how we can solve problems on SLE. Now, we take another example problem. Antimony and lead form a eutectic at 251 degree centigrade. So, temperature is given and 11.2 weight percent. So, weight percent of this antimony is given. Okay. The enthalpy of fusion and then melting point of lead are as follows. For the lead, they are given as delta H fusion is minus 5.1 kilojoule per mole, and then for the lead melting point is 327.5 degree centigrade. So, determine the composition of lead rich solid solution at eutectic. State any assumptions that you make. So, nothing has been given. So, it is actually mention lead rich solid solution at eutectic. So, actually one of the phase rich in one particular component, if it is mentioned like that, that means it is partially miscible system or partially miscible solid solutions are there. So, then ln small xi gamma I by capital Xi gamma I is equals to whatever that expression that we have to use, and then we have to find out what is this xi, capital Xi. Okay. So, this is the expression that we have to use. In this expression, whatever the things are there are provided or not, that we have to see. If not provided, we have to make certain kind of assumption. That is also clearly stated in the problem. So, let the subscript 1 designate antimony and 2 for the lead. So, at eutectic temperature, a liquid solution, an antimony rich solution and then lead rich solid solution are in equilibrium. All three phases are at equilibrium, that is the eutectic point. Okay. So, assume the solid solutions at the eutectic temperature exhibit ideal solution behavior, because nothing is given about the non-ideality of the solid phase, and then that is also possible. Further, we can assume the liquid solution is ideal since it is only 11.2% of antimony. So, it is a small fraction, it is there, not negligible, but small fraction only there. So, then we can say that the liquid solution is almost kind of pure solution, and then we can take the liquid solution is also as a kind of ideal behavior. So, from here capital gamma I is equals to 1, and then from here small gamma I is equals to 1. Okay. Then we have for both the component, if you write, we have these ones. Small gamma 2 is equals to 1, capital gamma is equals to 1, capital gamma 2 is equals to 1. We can also assume the change in heat capacity between solid and liquid phases is negligible. Delta CpSl is equals to 0, because no information is given. So, we have to assume there is no option. So, that second term in the RHS is gone in this equation. This relationship required to find the composition of the solid solution reduces to this form. Ln x2 divided by capital X2 is equals to delta H fusion of component 2 divided by R multiplied by 1 by T minus 1 by Tm of component 2, because we wanted to find out this x2. Okay. This is the final relation, and then we have to find out this capital X2, how much it is. This is given, this is also given. Okay. So, at the required temperature, we have to find out this capital X2, but what is this small x2, that is not given. But weight fraction of these two items are given. So, antimony is 11.2 weight percent. So, what we can have, we can convert them into the mole fractions and then get that small x2. So, here T is the eutectic temperature, okay, that is given, x2 is the mole fraction of lead in the lead rich phase, that is what we have to find out, and then find the mole fractions at the eutectic point from the mass fractions, whatever this 11.2 weight percent antimony and then remaining lead is there. So, that weight fraction basis we can use, but these are given in the weight fraction. So, we have to convert them into the mole fractions. So, how we can do? We need to have the molecular weight information about these components, so that we can get from the reference books. So, Molecular weight of antimony, it is not given from reference book, so we can get this one 121.76 gram per mole, and then molecular weight of lead is 207.2 gram per mole. Then x1 should be, because antimony we have taken as component 1, so x1 should be 11.2 divided by 121.76 and then whole divided by 11.2 divided by 121.76 plus 88.8 divided by 207.2, that comes out to be 0.177. So, that means x2 is 0.823. So, only unknown in the previous equation that is to be solved to get the capital X2 is this small x2, that is also now we got it. So, this if you substitute here in this equation and then give this eutectic temperature, this Tm2 is given and delta H fusion is also given, x2 you just obtain. So, from here if you write small x2 by capital X2 is equals to exponential of this delta H fusion 2 divided by R multiplied by 1 by T minus 1 by Tm2, and then from here x2 is nothing but small x2 divided by exponential of delta H fusion 2 by R and then multiplied by 1 by T minus 1 by Tm2. So, this is what we have. So, this is x2 is 0.823 divided by exponential of delta H fusion is minus 5100, it is given 5.1 kilojoule it is given. So, minus 5100, R is 8.314 and then eutectic temperature T is given and then Tm2 is given. So, all that you substitute. So, then you get 0.955. So, that means x1 is 0.045. So, in the lead rich phase, lead is very high, almost 95.5% by moles. Okay. This is how we can solve the different types of problems in SLE. We can take one more example problem. Example 3, bismuth and cadmium form a eutectic at 144 degrees centigrade and Xa is equals to 0.45. They are also completely immiscible in the solid solutions, completely immiscible in the solid solutions. They are also completely immiscible in the solid phase, that means pure solids we have to take. The melting points for these two components are given as 271 and 321 degrees centigrade respectively. The enthalpies of fusion of these two elements are minus 10.46 kilojoule per mole and then minus 6.1 kilojoule per mole respectively. Estimate 3 suffix molecules parameter based on these data. Let us say the liquid phase, whatever is there, liquid phase non-ideality, if you describe by 3 suffix molecules equation, whatever the 3 suffix molecules parameters A and B are there, that you have to find out. Neglect delta CpSL, that is Cps minus Cpl is 0, right. So, it is a pure solid system, that equations we have to take, pure solids in equilibrium with liquid. So, FAS is equals to Xa gamma A FAL and FBS is equals to XB gamma B FBL. So, this actually a reference state something like a knot we can have here, something like that, like this at reference temperatures. Okay. From SLE, that is when pure solids are in equilibrium with liquid, then we have this derivation ln small xi small gamma I is equals to delta H fusion at Tm divided by R multiplied by 1 by T minus 1 by Tm plus delta Cp SL by R multiplied by 1 minus Tm by T minus ln T by Tm. This is what we have. It is said that this delta Cp SL is negligible or neglected, that is what given in the statement. So, this part can be ignored. So, now if you write this equation for two components, component A and component B. So, ln gamma A, ln Xa gamma A is equals to delta H fusion T at Tma by R multiplied by 1 by T minus 1 by Tma. So, whatever ln Xa gamma A is there, that we can write ln gamma A plus ln Xa. So, that ln Xa, if you bring it to the left hand side, we have minus ln Xa. Similarly, for the second component, if you do ln gamma B is equals to delta H fusion at Tmb by R multiplied by 1 by T minus 1 by Tmb minus ln Xb. So, these two relations are there, right. So, here these delta H fusions are given, TMAs are given, TMA, TMB are given, and then T is also given, XA, X is also given. So, XB is also known. So, only thing that ln gamma A, ln gamma B are not known. So, for we do not need them, we need corresponding 3 suffix Margul parameters A, B. So, whatever the 3 suffix Margul's equations are there, so corresponding ln gamma A, ln gamma B equations we have to use. So, from 3 suffix Margul's equation, we have ln gamma A is equals to A plus 3b by RT xb square minus 4b by RT xb cube, and then we have ln gamma B is equals to A minus 3b by RT x square plus 4b by RT x cube. So, now in place of this ln gamma A, you substitute this one, and then in place of ln gamma U, in place of ln gamma B, you substitute this one. Then what we will have, are substituting or maybe equating this equation 2 and 4, and then equation 3 and 5 if you equate, then we have ln gamma A is nothing but A plus 3b by RT xb square minus 4b by RT xb cube is equals to right hand side of equation 2, that is delta H fusion Tma by R multiplied by 1 by T minus 1 by Tma minus ln Xa. Then equation number 3, that is ln gamma B is equals to we are having. So, ln gamma B is nothing but A minus 3b by RT Xa square plus 4b by RT Xa cube for 3 suffix Margul's equation, and then is equals to right hand side whatever we have delta H fusion Tmb by R multiplied by 1 by T minus 1 by Tmb minus ln Xb. So, here we know this Xa is given. So, Xb is also be known, Tma is given, Tmb is also given, eutectic point temperature T is also given. So, in this equation everything is known except A and B. So, we have 2 equations. So, in these 2 equations except A and B, you substitute all these values here. So, then A plus 3b, when you substitute all these values in equation number 6, you will get A plus 3b 0.55 square minus 4b 0.55 cube divided by 8.314 and multiplied by 417.15 is equals to minus 10,460 divided by 8.314 multiplied by 1 by 417.15 minus 1 by 544.15 minus ln 0.45. Then these values if you substitute in equation number 7, then we have A minus 3b 0.45 square plus 4b 0.45 cube divided by 8.314 multiplied by 417.15 is equals to minus 6100 divided by 8.314 multiplied by 1 by 417.15 minus 1 by 594.15 minus ln 0.55. So, these 2 equations we are having, and then these 2 unknowns A and B are there. So, if you solve these equations, 2 equations, then you will get A as 1157 joule per mole and then B as minus 90.3 joule per mole. So, 3 suffix modal parameters A and B you can obtain like this. Like this, different types of SLE problems can be solved using the equation or equilibrium relation that we have established in the previous lecture. Okay. So, the references for this lecture are Engineering and Chemical Thermodynamics by Koretsky, Molecular Thermodynamics of Fluid Phase Equilibria by Prof et al., Chemical, Biochemical and Engineering Thermodynamics by Sandler, and an Introduction to Chemical Engineering Thermodynamics by Smith et al. However, this entire lecture is prepared from this reference book, Engineering and Chemical Thermodynamics by Koretsky. which is an excellent book for SLE problems. With this, we have completed all the lectures of this course, Advanced Thermodynamics. Thank you very much for your attention. Thank you.